So we are very happy to have Spela Spenko, who will tell us about the Frobenius morphism in invariant theory.
Yeah, thank you very much. So this is a joint work with Theo Ratschilders and Michel van den Berg. And so let me first start with some general setup and motivation. Yeah, so we assume that K is an algebraically closed field of positive characteristic. And we take a reductive G denotes a reductive group. So for example, a finite group or tori or some classical groups, for example, SLN and GLN. So in what follows, we will be basically only interested in SL2. Yes, sorry. Yes. Was there a question? Or no?
I don't think so.
Okay, sorry. And we take for W, we take a finite dimensional representation of G. And then we look at the symmetric algebra on W. We will denote this by S. And so in this symmetric algebra, G also acts. And with R, we denote the invariant ring. Okay. And then mostly in this setting, we will be studying the Frobenius morphism. So we have a Frobenius morphism which sends from R to R, which sends R to the P. And so the main general problem in this talk will be to describe R as a graded R to the P module, or we can also take the higher
Uh-oh. Spela, we seem to have an internet problem.
Yes.
Okay, hopefully it'll resolve itself in just a moment. Oh no, I think we lost her. Okay, I'm going to pause recording. I think you can go ahead and start again whenever you're ready.
Okay. Yeah, so this is equivalent to describing R as a the equivalent to describing the overing of p roots of I, or p to the e roots of I, as an R module. Okay, so by this description, so what we mean, so which we would like to understand which summands, which indecomposable summands appear in this description, then also how this summands depend on E, so on the depend on E, and how many summands do we get if we vary E? So in particular, so do we get finitely many of them, or infinitely many? So this will be somehow the main problem that we will be trying to tackle in this invariant setting, which will actually become even more specific. So what is the problem seems rather natural at its own, but there is also some motivation hidden behind. So let me first mention motivation that comes from differential operators. So there is a classical conjecture due to Levasseur and Stafford, and this is in this conjecture is in characteristic 0, and other notation is as above. So in particular, so we have a reductive group, representation of it, and then the R denotes the invariant ring of the symmetric algebra on W. Yeah, it's okay. I will try to share the data maybe. Yeah, I apologize. The setting, they conjecture that the ring of differential operators DKR is a simple ring. And so this was shown in several cases. So Cantor showed it for finite groups. And then Masson and Michel, they showed it in the case of tori. Then Michel also showed it for some classical representations of for some SL2 representations, so some classical, yeah. So some SL2 representations, and Levasseur and Stafford, they did it for some classical representations of classical groups. And then Karen Smith and Michel had an idea to try to prove this via reduction mod P. So Smith. Back, so. And in this case, there is a very nice description of the ring of differential operators due to Chase. So now we are back to a characteristic, positive characteristic. And in this case, the ring of differential operators can be, okay, sorry, can be described as the union of the morphisms ring of R as a module over to the R to the P to the I. Okay. So this gives us a connection with Frobenius morphisms, and then they defined the following property. So this definition is again due to Karen Smith and Michel, so that R has a finite Frobenius representation type, also abbreviated as FFRT. So if there exists a finite, basically if there are finitely many Frobenius summands, also if we take into account all E. So if there exists a finite set M of R modules, such that the overring of P or P to the E roots of R as an R module is isomorphic to direct sum of summands in M, and this for all E. So that is a generalization of a finite representation type. And then they were able to show that. So they showed that if R is strongly F regular, so a generalization of F regularity, and if it has finite Frobenius representation type, then in this case, the ring of differential operators is simple. Still everything in characteristic P. So then, moreover, so what they also showed that this that some rings of invariants have this FFRT property. So they showed that if that this is true for the ring of invariants for linearly reductive group. So if G is linearly reductive, so this is an extension of a finite group by a torus. So then in this case, the invariant ring is a finite Frobenius representation type. So this was one motivation that motivated also the definition of this finite Frobenius representation type. And then another motivation comes more from non-commutative geometry, and it's about non-commutative resolutions. So what is a non-commutative resolution? So non-commutative resolution is of the form in the morphism in the morphisms of some R module M. So this is this algebra is a non-commutative resolution NCR of R if M is a reflexive R finitely generated reflexive R module, and if it has finite global dimension. M is fine. And then the natural question is, so do the Frobenius summands or do they give us maybe this module M? So do they give rise to a module M such that this algebra would be a non-commutative resolution? So is the endomorphism ring of the P to the ith roots of R as an R module, a non-commutative resolution of R. And again, this is true in the case that G is linearly reductive. So this was this was shown by us, but then there was also an independent proof by Faber, Müller, and Smith. They used a different method. So in this case, the Frobenius push forward gives us a non-commutative resolution of R, resolution of R for. We need to take a sufficiently big E. So, and this is in the setting if G is again linearly reductive. So basically in the toric setting. Okay. So that was the second motivation, and then the last motivation is more in the geometric setting. So in the setting of tilting bundles. So one can also study this Frobenius morphism in the geometric setting. So assume that X is smooth and proper variety, and then we look at the Frobenius morphism, and then we would like to describe the push forward by the Frobenius morphism of the structure sheaf. So this has been done in several cases. So Rao did it for Pn. So the composition of the Frobenius push forward and higher Frobenius push forwards of the structure sheaf on P to the n. Then Achinger and Langer, they did this for smooth quadrics. So Q, where Q is smooth quadric. Bondal did it for some toric Fano trifolds. And then Samokin for some partial flag varieties. And so what is common to all these cases is that in all these cases, it turns out that the Frobenius push forward of the structure sheaf is tilting. So maybe let me recall what a tilting bundle or a tilting sheaf is. sheaf is tilting. If it has no higher self-extensions, and if it generates the derived category of S. But already this property of not having higher self-extensions is quite special. So the question is this a general phenomena? So is the Frobenius push forward of the structure sheaf, is it always tilting? So in particular, we could ask this for the approach of the invariant ring, if it's smooth. R is. Okay. So that was somehow a general setting and motivation. And now we come to the specific case. So in our specific case, G is SL2. She also writes a special linear group of some vector space V, where the dimension of V is equal to 2. And W, for W, we take n copies of V. Hence, we also write this as V tensor F, where dimension of F is equal to n. And again, as in the beginning, we take for S the symmetric algebra on W, and R is the invariant ring. So note that in this case, R is actually the homogeneous coordinate ring of Grassmannian GR to n two-dimensional spaces in an n-dimensional space, which we also view as GR to F, for F as above. Okay. Maybe let me briefly sketch why that's the case. So if we have an n tuple of vectors in V, so they have two components, each of these vectors, and then we can view rows as two elements in F, and this n-dimensional vector space. And so how is the action? So the action is we have a diagonal action, so we act on each of these VIs. And so what does this mean for the action on the F1 and F2? So we get that this is F1 G transpose, and here we have F2 G transpose. Okay. So in particular, if we look at the vector subspace of F spanned by these two elements, this subspace is preserved by the action of G. And now if we look at the closed orbits in W for the action of G, so we get that they correspond to, so we have closed orbits either get to the trivial subspace or to the two-dimensional vector subspace of A. And so the invariant, the closed points in the invariant ring, they parameterize closed orbits, and they are indeed in correspondence, except for 0, with this two-dimensional vector subspaces of F. So closed points in the Grassmannian. So in this setting, we are then able to find the composition of the Frobenius push forward. So we are able to find the composition of push forward as a graded R module. So in the case when we look at just at the E equals to 1, in this case, we are also able to describe the multiplicities and grading shift, and there is no restriction on P, while for E bigger than 1, we need to assume that P is big, is sufficiently big. So the bound is n minus 2. So here we have, W is n copies of V, and P is bounded with respect to this n. And then also in that case, we don't describe we don't give the multiplicities, and so everything is up to multiplicities and grading shift. Okay, and then what do we get as corollary from this explicit description of the Frobenius push forward? So we get that R indeed satisfies the FFRT property. Again, here we need to assume that P is greater or equal to n minus 2. So in particular, we get that the ring of differential operators is simple using the result mentioned above from Smith and Vandenberg. And then also the Frobenius push forwards, they give us NCRs. So this is, sorry. This is an NCR of non-commutative resolution of R. And again, so if E is bigger than 1, we should restrict to P greater or equal to n minus 2. And moreover, the Frobenius push forward on the structure sheaf of approach R. So in the geometric situation, in the geometric setting, the situation is a bit less favorable. So this is not often tilting. It's actually tilting bundle is actually very rarely tilting. So it's tilting if and only if n is equal to 4 and P is bigger than 3. Okay. So maybe it would be now a natural stop. I don't know. For the rest, I will describe where one can look for the summands and with the strategy of the proof. Or I could also continue.
No, I mean, maybe if you want to stop now, it's totally okay. Or maybe Shri can take over. Shri.
Yeah, we can stop now for a few minutes, and let's say 5 minutes. Why not?
Okay.
What time?
Let me start recording. Go ahead.
Okay, so now we will describe what the summons are. So first, where should we look for the summons? So for this, we have the following remark is that Frobenius push forward is it's a Cohen-Macaulay R module. So what we need to do, we need to find some natural choices of Cohen-Macaulay R modules. And so because we are in the setting when R is an invariant ring, so then it's natural to first look at the modules of covariance. So if U is a representation of G, finite dimensional representation of G, then the module of covariance is defined in the following way. So we take the tensor product of U with the symmetric algebra on W. So we have an action on G on that, and we take the invariance. And this is a module over the invariant ring, and that's called a module of covariance. And so we need to characterize to determine when these modules of covariance are Cohen-Macaulay. And one can do that. So it was done in characteristic 0 already a long time ago by Michel, and then we do it in characteristic P. And so module of covariance of the symmetric power of V is Cohen-Macaulay if and only if I is between 0 and so I symmetric Cohen-Macaulay module associated to I symmetric power of V is Cohen-Macaulay if and only if I is between 0 and n-3. So here a bit of caution is needed because that holds in the case that P is greater or equal to n-2, and to make this work also for other P, we should replace this the symmetric power of V by another representation, so-called tilting representation. So let me mention what that is. So first with f of nabla, we denote those SL2 representations that have filtration with the symmetric powers of V. And then in the F delta, with F delta, we denote the dual of F nabla. And then the tilting representations are those that have a filtration by the symmetric powers of V, and also their duals have such filtrations. So tilting SL2 representation is defined, so they lie in the intersection of F nabla and F delta. And so, and the indecomposable tilting representations, they are labeled by natural numbers. Indecomposable. So they are labeled by n. So for small i's, the tilting representation corresponding to I is the same as the symmetric symmetric power of V, and small I meaning small in terms of P. So if this is between 0 and P minus 1, and then, for example, the tilting representation, so TPV corresponding to P, is an extension of SPV by SP minus 2V, etc. Okay. So, and for this to be for this result to be correct, also for small p, we need to replace the symmetric power by Ti, and then we don't need anymore this assumption. But it turns out that this Cohen-Macaulay modules of covariance, they don't give us enough of Cohen-Macaulay modules. So we need to look for some extra Cohen-Macaulay modules. And for this, we find some inspiration in the geometric setting. So if we denote by X the approach of R, so the Grassmannian, and here we will have, instead of two-dimensional subspaces, we will take two-dimensional quotients of F, Grassmannian. Quotients of F. And with Q, we denote a universal quotient bundle. So it's of rank 2. And with R, we denote universal subbundle, which is of rank n minus 2. And then we look at we have a tautological short exact sequence. So we have R, which embeds to F tensor with the structure sheaf, and then the quotient is Q. And then the first thing that we may maybe wonder about is, so to what correspond modules of covariance on the geometric side. So take the module of covariance corresponding to the ith symmetric power. This corresponds, I am omitting here the grading shift. So corresponds to the ith symmetric power of the quotient bundle. So the module of covariance is can be obtained from the global sections of the shifts of the symmetric power of Q. And then, yeah, we may just also take instead of taking the symmetric power of Q, may take the exterior powers of the universal subbundle. So then this will give us another R module, and so we will show that this R module is Cohen-Macaulay, but so we have then another. It's a Cohen-Macaulay for for J in an appropriate suitable range. But again, this will still not be enough. We still need more Cohen-Macaulay modules. So how we will obtain those? So we look at the right part of this short exact sequence, and we take the symmetric power of it. So we take F tensored with the structure sheaf to Q. So Q lives in degree 0. This one lives in degree -1, and then we take the J symmetric power. So what are the terms in this complex? So we have the J exterior power of F tensor with O. Then we have the J minus first exterior power of F tensor with Q, etc. And then at the end we have the J symmetric power of Q, and this complex is exact except in the degree minus J, where in degree minus J, and there the cohomology is given by the J exterior power of R. And so now we can take the can apply the global section to this complex and shifts of it. So what do we get? We get a complex. So we denote the morphisms. We use the same notation. And then so here we have a module of covariance corresponding to V. And at the end, we get the module of covariance corresponding to the J symmetric power of V. And again, it turns out that this complex is exact, except in the degree minus J, where its cohomology is given by this R module that we introduced, Kj. That corresponds to the J exterior power of R. And so what do we find is that so Kj, which it's the kernel of this last or first morphism. So this has a resolution. It's in an exact sequence where has a resolution by the modules of covariance, where I is between 0, and J. So what do we find from this is that Kj is indecomposable Cohen-Macaulay for J between 0 and n-3. And then we can also look at the kernels of the other morphisms in the complex, and we can use the same argument to show that they are also indecomposable Cohen-Macaulay modules. So this is for J between 0 and n-3. and k is smaller or equal to j. Okay, so yeah, let me mention that in the case that characteristic is small, so smaller than n-2, this needs a slight tweak, but it still works. Okay. So now we can finally describe or tell which summons appear in the Frobenius push forward. So yeah, we will first assume that P is greater or equal to n-2, and then I will make a comment later what holds without this, what still holds without this assumption. So R, as already says, satisfies this, has a finite Frobenius representation type, and so the modules that appear as Frobenius summons are, so we have R, then we have modules of covariance, then we have these KJKs, and they are duals. And so here k is smaller than j, which runs from 1 to n-3. So that are the summons that we get. So first remark is that if we just look at the first Frobenius push forward, then in this case this has only summons of the forum, so it has modules of covariance, and then it has these KJJs. So in this case, we don't need the other KJKs. Okay. And also in this case, there is no need. I mean, there is no restriction on P. But we need to replace this module of covariance corresponding to the symmetric powers of V by the module of covariance corresponding to tilting representations. And then, so when does it stop? So when do we reach all the Frobenius summons? It actually stops already at the second steps. So the Frobenius push forwards, they have the for E greater or equal to 2, they have the same summons. And here everything is up to multiplicity and grading shift. Okay. Now let me mention what the strategy is to find this decomposition. So we crucially use the fact that R is an invariant ring. And yeah, not just any invariant ring, also that it's invariant ring for an SL2 representation, because in this case we have a very, very good, in this case there is a good understanding of the representation theory. Okay, and so what do we want to do? So we want to pass from an R module to a G equivariant setting, so to an S. To an G equivariant S module. So for this, we first need a bit of notation. So with G1, we denote the first Frobenius twist of G. So G in our case is just it's SL2, and so in this case, then the Frobenius morphism becomes linear over K. And with G1, we denote the kernel of Frobenius, this Frobenius morphism. So this is the first Frobenius kernel. It's an infinitesimal group scheme. So just maybe to give an example. So if G is the additive group of K, if GA is the additive group of K, then this first Frobenius kernel is spec of K of X mod X to the P. Okay. So now we can state this passing from a module over R or R to the P to the G equivariant setting. So we have inverse symmetric monoidal equivalences between, on one side, reflexive R to the P modules, and on the other side, reflexive G1 equivariant S to the P modules. And so how do we go from left to right? To go from left to right, we need to first tensor with S to the P over R to the P. And then, so because we want that the output is a reflexive module, we should take a double dual. And then to go back, we just take the G1 invariance. And so now so what do we want to do? We want to describe R as an R to the P module. So we would like to describe it in the equivariant setting. So where is R sent to? It's sent to the invariance of S for this first Frobenius kernel. And then, so how we view this first Frobenius, the invariance for the first Frobenius kernel of S, we view it as the zero cohomology of the following complex, which computes homomorphisms with respect to G1 action. And so this complex we view as an element. It's a complex in the derived category of G1 equivariant S to the P modules. Okay. So we will try to understand this invariance of S for the first Frobenius kernel by somehow trying to understand this complex a bit better. And maybe an first an observation from a homological algebra that will, in some sense, lead us also to then this setting. So first, what happens? If we forget the action? So then, if we have a complex, assume that we have a complex of 3 SP modules. And we assume that is exact except in this boundary degrees. So except in degree 0 and r. So it's HIM equals to 0 for I different from 0 and r. And then in this case, we can describe the zeroth cohomology in terms of the r plus first CCG of the rth cohomology of M, up to a free summand, so up to a free SP module. And it turns out that somehow one can adjust this also to the equivariant setting, but then we need to impose, so some conditions needs to be satisfied. So if the following conditions are satisfied, so we should have that the first truncation of this complex is formal in the derived category. And then we should also have that this cohomologies for the first Frobenius kernel of S, they are good, they are well-behaved G1 representations. So representations for the first Frobenius twist of G. So we want that they have a good filtration. So what does this mean? It roughly means that they have filtration, but it can be infinite. It's a bit more general than this filtration by this symmetric powers of V. Roughly. And then there are some other more technical conditions that need to be satisfied. So if that's the case, then we can do this similar procedure as we did with this this homological algebra observation, that we can write the zeroth cohomology as the sum over the CCGs of higher cohomologies. And then we also have some, so this is up to a free summand, but so here free summand means that we also need to, there is also some extra representation of G1. So T here is a tilting G1 representation. And so when we then apply the invariance, we get that R is direct sum. So this these CCGs will correspond to the KJJ, so the modules that correspond to the jth exterior power of the universal subbundle, and then we have from this free part we will get modules of covariance. Okay. And then, yeah, let me just say that so this was everything for the first, so for the first Frobenius push forward. But if E is greater than 1, then one needs suitable generalization of this. So yes, of this, mainly of the first one. And then the verification of this verifications of these conditions is more involved. Okay. Thank you.
Thank you, Spela. Any questions? You can actually, yeah, I can unmute and speak or just post it in the chat.
So maybe you can ask something.
Sure, of course.
Go ahead. Thank you. In this strategy, I got a little lost, but I am curious where exactly the fact that GSL2 comes in. Where is it important?
Yes. So what do we want to understand? We want to understand this. So SP modules were G equivalent S to the P modules, basically, or G equivalent S modules to make it simpler. And there it's very important that it's SL2, because in this case, the representation theory of SL2 in positive characteristic is well understood. While if we go to bigger SLS, already it's the representation theory gets much more complicated.
I see, but for example, this description of the invariance of G1, you had like a direct sum over the CCGs of. So here, is this true for any G or only for SL2?
No, this is true only for SL2, and it's a more general setting. So it's a setting if this is formal, and this is easy to verify in this, easy to verify in the setting of SL2, and then if this condition is satisfied, which is also not, I think, not so obvious for more general groups, etc. And there are some other conditions that need to be satisfied. So if that is satisfied, then we have this decomposition. But to show this, the most difficult is actually this first part, to show this, that this complex is really formal. Here we really use that we have SL2, we actually use exactly which representation we have, not only that we have SL2.
Thank you so much.
So you have stabilization of the factors of the decomposition at the second push forward, you said, right?
Yes.
Is that something you expect for Grassmannians for higher M, or is that maybe special to the SL2 case?
I think it came to us with quite a surprise, but I don't know. I don't know if there are expectations for higher Grassmannians. I'm not sure.
Thank you.
Any other questions? It looks like not. Thank you, Spela, again for doing this. I know it's already rather late, so we should let you go.
Thank you
Goodbye.
very much. Thank you.
Thank you.
Thank
Bye,
you.
everybody.
Thank you.
Thank you.